All right. The other day, I did some examples. I did an example where we're doing Thevenin, and I have a feeling you guys are going to want to look at the equivalent circuits and stuff like that when we get into recitation today. But I want to look at the whole node voltage method. We talked about this the other day. We started talking about it at least, right? So when I look at this and I do node voltage method, I'm solving for voltages at nodes, right? But what kinds of equations am I writing? I'm writing current equations and solving for voltages. All right. So that's important to remember. So in terms of the way that I did this, right? So I talked the other day about the concept here basically is if a circuit has n independent nodes, right? I have to have n equations always. All right. I have to have as many equations as I have unknowns. You guys got to be really careful when you do this and make sure that when you look at your equations, they better all be currents. All right, unless I have a supernode, in which case there's going to be something that relates voltages. All right, but check the units on these things. All right, when you guys, I see all the time, especially when I give supernodes, I see amps minus amps equals volts, right? Think equations that don't make sense. So we're going to talk a little bit more about that. Each node has a voltage with respect to ground. That's different than the voltage across an element, okay? And we end up writing a set of current equations to solve for everything. So what I talked about there the other day is voltage is always measured with respect to something, or okay, there's got to be 2 points anytime I talk about a voltage. So if I talk about a node voltage here, I've got V1 and V2, right? V1 and V2 are the voltages above ground. All right, so the way that I sort of think about this then is if I were to do a KVL, let's say, around a loop here, let me try to make some sense of this. So no, let me do that when we get to supernodes. All right, I'll take a closer look at this when we do supernodes. But basically, V1 is the voltage with respect to ground. V2 is the voltage at this point with respect to ground. All right, now I labeled here, and you should too, VA, VB, VC, right? And then whatever voltage I guess I would have, I'll call it VD, I guess, across that resistor. All right, and the way that I always think about things is I write them in terms of the way that I think the currents are going to flow. And then I work out the details from there. Now, I know I'm going to talk about the Zybooks approach. The Zybooks approach says assume everything goes out. I don't like that approach myself. Totally fine if you use it, you'll get the same answers as what I do. All right, I'm going to show you that here in a second. But if I'm doing this, the reason I write the voltages across those things is it's important to me because I can say, if I look at VA right there, the voltage across those two resistors, I can say that that's got to be, actually, I'm going to write it this way. I'm going to write my Ohm's law and say I2. How do I write I2? Yeah, VA over R2 plus R3. That is an Ohm's law. So this is my process. This is an Ohm's law statement that I just wrote for a resistor, okay? I can transfer that Ohm's law statement into something that relates to the node voltages, right? In other words, if I did a KVL around, let's just, for grins, let's do a KVL around this loop here, okay? If I do a KVL around this loop, so the left side loop, I would get 0 equals negative V0 plus VA plus V1. And so I see with that VA has to be equal to V0 minus V1. Okay. So so what I did here is I just defined the voltage across that resistor in terms of the node voltage. All right. That should always be the case. And I think about this in terms of when I'm looking at the voltage across that resistor, I say it's the plus terminal node voltage minus the minus terminal node voltage. All right. And that came from a KVL statement that I just wrote there. All right. I did a KVL around that loop. And this is entirely consistent with what I see around that loop. And I could do that for all of them. Okay. So the next step for me is to then just use that result, basically to say replace VA with V0 minus V1 over R2 plus R3. And then what would I do for what I've called I3 here? It's the voltage across what resistor? R1. So I called that VB. So I divide VB by R1. And VB, again, if I do the same thing here, the node voltage at the plus terminal minus the node voltage at the negative terminal, that would be V1 minus 0 over R1, right? And then I can do the same thing. So I4 would be V sub C divided by R4. Well, that would then be the voltage at the node voltage at the plus terminal minus the node voltage at the negative terminal divided by R4. Right, and then I would have at the, for what is it, for R5, I5 is what? I labeled it VD, that's the voltage across the resistor, divided by R5. And then I put the voltage across the resistor in terms of the node voltages. So what's that voltage at the plus terminal minus the voltage at the negative terminal? What's that? For I5. V2 minus 0. Okay. Now, there is no relationship that I do for this branch over here because that's a current source, right? He's fixed, he's pinned. All right, so if I say at node 1, and then I'm slow about this. All right. You guys look at what I do, it's slow. You guys try to skip right to the step of what I'm about to do, which is to put one equation in terms of the node voltages. I'm slower, but I'm faster. I take more steps, but I do it faster than you. I guarantee it. Right. You guys try to jump right to that step, and I guarantee you're going to make all kinds of sign errors when you do it. All right. Take it slow, and you're guaranteed to get it faster. Right. I define those currents just in terms of Ohm's law, then put them in terms of the node voltages. Then I do my KCLs and put it all together. So node 1, what's my KCL equation here? In terms of the currents that I've defined in that picture, what's my KCL? Yeah, so the currents going in is I2. That's equal to I3 plus I4. That's as in terms of the way that I defined it here. Now I'm going to square it up with the Zybooks approach where they have them all going out here in a second. But in this case, based on the way I defined them, I2 equals I3 plus I4. I think of it as in equals out. All right. So, and then I plug in here, what is I2? Well, I2 is V0 minus V1 over R2 plus R3. That has to equal, I need to give myself more room to write this. Let me get rid of this down here. All right. So I2 equals I3 plus I4. I2 is apparently V0 minus V1 over R2 plus R3. I3 is V1 over R1. And I4 is V1 minus V2 over R4. Okay. All right. Now, one thing I'm going to show you is something I showed in office hours last night to a very small group of people that came, but basically how I group this into MATLAB. All right, because I try to spend a lot of time simplifying this guy. I try to get him so I can identify coefficients, and then I map those coefficients into the matrix. Right. That way, I like being able to see everything carefully, rather than trying to simplify the math. Just look at it rather than simplify it. Okay. So I've got that result. Somehow that should be able to square up with the Zybooks approach too. So in the Zybooks approach here, this is what they did, right? They look at this, and so I took this example right out of there. So they have I2, I1, and I3 all going like that. This drives me nuts because then I have two currents going the opposite direction. Or was it that my brain doesn't like that? All right, but if this is what you're comfortable with, it's fine. All right. what they then do is basically say, if looking at this, all of my equations are going out, all my currents are going out. So in other words, I sum all those together, I have out equals in. Nothing's going into node one. So I put I1 plus I2 plus I3 all equal to 0. All right, you guys follow that? Okay. So when I look at that particular equation there, all right, what they then do is they say, okay, well, I1, I guess just to be clear, the way I put these in here, this is I2, this is I1, and then I3 is here. So this is I2, this is I1, and this is I3. Now, what they do in their approach is if you do it this way, then basically what you do is you define the current here for this guy is always, it's always the voltage at the node it's leaving from minus the voltage at the node it's going to. All right, so you look at I2 there, I2 starts at node 1 and it goes to node 0. So it's V1 minus V0. For I1, it starts at node 1 and it goes to ground. For node 1, it starts at, so for I3, I guess, it starts at node 1 and it goes to node 2. So it's V1 minus V2. This is the equation the Zybooks way gets. All right, if you look at what I got, so let's put it here. So I got V0 minus V1 over R2 plus R3 equals V1 over R1 plus V1 minus V2 over R4. That's the value that I got over here. All right, so this is mine. Zybooks was V1 minus V0 over R2 plus R3 plus V1 over R1 plus V1 minus V2 over R4. Okay, this is Zybooks. I would argue that those are the same. Right? How do I know they're the same? Well, I'd have to move the V1 minus V0. So in other words, this guy here, if I move that in mine, that term over to there, it would become minus V0 minus V1, which becomes V1 minus V0. It's entirely the same equation. All right. Mentally, I like my approach better. It's my approach, I guess. Right. But it's a little bit more intuitive. Different books teach them differently. Zybooks kind of likes to take that approach. One of the reasons I don't like this is then when I do something like at node 2 in this Zybooks approach would be I4 plus I5 plus I6 equals 0. What would I6 be in this approach? Negative IO. I don't like that because I know it's going, it's telling me it's going into the node. I'd rather just use that, right? For me, it's a little more intuitive, but whatever you're comfortable with, it's the same equation, right? And that's the important thing, right? Is it works out to be the same equation. All right. So one thing where this gets hard, where you guys screw up, is we get this idea of supernodes. All right. Now, what the heck's so hard about a supernode? Why is a supernode hard? What makes it hard?
Polarities and bigger we put like right?
You get into specifics on me, right? Just at a high level, what is it? What is node voltage? The node voltage method, what are we solving? What kind of equations do we write in the node voltage method? KCL, we write currents. Now that works for us really well when I have a circuit like this guy, because in each of these branches, I just have resistors. So how do I define the current in a resistor? Ohm's law, right? Ohm's law tells me that it's voltage divided by resistance is the current. When I get something like this, if I write a KCL for each of these branches, it's easy to write my I2 right here. It's a little tricky to write my I5, right? How do I write that relationship in terms of the voltages? I can't, right? If I have a voltage source, what's the current in a voltage source? you don't have any way to define it. It's not, it could be 0, could be a mega amp. We don't know, right? The rest of the circuit defines it for us, right? The voltage source just provides whatever current the circuit asks for. All right, that's the important thing about it. It has a fixed voltage, but its current's defined by the circuit. The opposite is true for a current source. For a current source, you know it's current. The circuit determines the voltage across it. Okay, so there's no way for me to relate. So voltage and current are what I call the terminal variables. If I have a component, so if you go to the lab and you grab a resistor, the resistor has 2 leads, right? Those are its terminal. There's a terminal relationship that relates the voltage and the current. For a voltage source, no such relationship. All right. You know the voltage, you got to figure out the current. Okay. So the way this looks, if you look at the way I problem 1 on the first exam had a super node. Actually, it had a super node with 2 voltage sources. I solved it the long way, which is basically to say that whatever current goes into one side of the voltage source comes out on the other side. All right, so what I'm going to do is I'm going to try to write this out. So help me out. I've defined the current here, I5. I have no way of defining I5 in terms of resistors or anything, but I can define it to be the current through that thing. So at the V2 node, in terms of the currents, the 3 currents I have there, I1, I2, and I5, what would be my KCL relationship? So at node 2, what would be the KCL right there? What's that? On node 2.
1 plus.
So I1 is going in. What's going out? I1 equals I2 plus I5. Okay. I1 equals I2 plus I5. All right. What about at the V3 node there?
I5 equals I4. I mean, yeah.
I5 equals I4 plus I3. Right? Now, what I can do is I can combine those 2 equations. Right? So I plug I5 into here. So I have I1 equals I2 plus I3 plus I4. So in other words, whatever current was going in here goes out here, here, and here. So in other words, what we say is we can think of that node 2 and node 3 as if they were one node, right? I don't like this idea of a super node because to me, this is just a fairly straightforward thing to think about. If I know my KCLs, this is straightforward. Basically what it's saying is any current that goes into one side of that voltage source, by the laws of nature, has to pop out again on the other side, right? None of the current gets eaten up inside of that voltage source, right? So basically what I get is I can say, I just need to know what's going in one side has to go out the other. All right, that's the way we use the supernode relationship. And then I1, I2, I3, I4 can all be defined in terms of the node voltages and stuff like that. All right, now the relationship that we have, let's say this was my my ground node. I'll do it here, right? Do it separately here for a second. Let's say this was my ground node, all right? The other relationship that you get when you have supernodes is you end up making a relationship between the 2 nodes that are connected to each other by a voltage source, all right? I can figure out that relationship by KVL, can't I? Right? Let's do a KVL around this loop right here. So I have 0 equals, what's the voltage across the resistor? So as I go around, what's the voltage across R3? Negative V2. Then I go minus 10. And then I go plus V3 to ground, right? Like that, right? So what do I get? I get 10 equals V3 minus V2. That supernode relationship is a KVL around the loop. All right, it seems magical, right, to you. You just know that that's the relationship, but it came out of a KVL. Everything is KVL and KCL, right? Everything. All right, so that's my relationship. So basically what I do is I use that voltage relationship. That gives me one equation. And then I basically just pretend like these are one node because, as I just said before, whatever currents are going into one side have to come out the other. Right? So basically I can say, I just pretend as if the voltage source isn't there, and I brought 2 and 3 together, and I just treat them as if they're one node. All right. I don't like that. If it's me, I would just probably do it the way that I did there. Right? And I would write one equation for node 2 and one for node 3. All right. But that's not the way that people like to do it. So all right. I want to use an example here where we go through that approach. And I grabbed a bunch of papers off my desk and did not grab the one I wanted to, which has the answers for this. All right. But I think I've got the answers here in my slides still. All right. So I want to do nodal analysis here. So a typical thing to do, you don't have to do it, but typically we make the bottom node the ground node. Could be, I could put the ground node there. All right. But it would be weird. Okay. Is this a node right here? It's not really. It's not an independent node. I don't know. I should probably know my network theory better and say it probably has some terminology like a subordinate node, or I don't know what it's called, but it's not an independent node that I would solve for, because whatever current I have here and whatever current I have here are the same. So I basically think of the combination of the 1 ohm and the 10 millifarad as one impedance. And I write one KCL equation for that branch. Okay. All right. First things first with this, I have to do my analysis in the phasor domain, but I have given this to you in the time domain. Right? If I've given this to you in the time domain, what do I have to do? I had to get it to the phasor domain, right? So that let's say I called this guy I sub s and I called this guy V sub s. All right, what's the phasor for VS and IS? What are those phasors? What's the phasor for 2 cosine 100t? For 2 cosine 100t.
Oh, I mean,
two angle 0. All right, and you told us, yeah, for 6 cosine 100t minus 30 degrees, it would be 6 angle negative 30. Yeah. All right, so I've got my 2 phasors. Yes, sir.
Is that angle kind of name? I always call it phasors, that reminds me of phasors, but is it like angle? Is that the way?
Well, so we say 6 angle negative 30. Sometimes we call it the phase. We don't usually say 6 phase negative 30. We say 6 angle negative 30. We call it the phase angle because it's the phase angle of the corresponding cosine wave. Okay. Yeah, all right. Well, so then also, what's the other thing I need to do to go to the phasor domain? There's one other step, technically. Yeah, my capacitors and inductors need to go to impedance values, right? So that means 1 over j omega c and j omega l, right? So, and what's the omega that I have here? Yep, 100 radians per second. All right, so if I look at this, I'd have j omega l. That would end up being j times 100. 10 millihenries, what's that? That's 10 times 10 to the negative 3, right? And then for the capacitor, I would have 1 over j omega c. And that would be 1 over j, what? What would that be? 100. What would I put for the 10 millifarad? Ten times 10 to the negative 3. Yeah. Or 10 to the negative 2. Okay. All right, so that's what I put in there for that. And so the way that I do this is I do all my analysis now, assuming that this guy becomes, I write that as Z sub L and I write that as Z sub C. Okay, like that. And I think I call the other two Z sub R because they're both 1 ohm. All right. So, all right, I want to go ahead and do this guy using the nodal method. All right, and I want to solve for V1 and V2, which are the phasors for those undefined nodes right there. All right. For me, where I start with this is, as I said, I like to define all my currents and stuff. All right. So what I do here is I say, all right, I'm going to define a voltage across that series combination, because technically what I have here is one impedance, right? I put this all in the phasor domain, but I should be able to write it like this. Here's V sub S. I'll call this R. It might be a little easier to view it like this. Right? What I've done is I've lumped the inductor and resistor and the resistor and capacitor together because they're in series with each other. There's just one term there. So that makes it a little bit easier for me, at least, to kind of think about this. This is V2, this is V1, and this is VS. Now, what I do is I then basically say, what's the voltage across here? What's the voltage across these guys? They're the same, aren't they? Right? And then I define a set of currents for myself. So what did I do? I called this current here I1. I called this current here I2. This current here was I3. And then this current here is I4. Okay. Now, what I want to do for myself real quick is I want to define, for all of my impedances here, I want to define my Ohm's law setups, right? So for me, I say, okay, I1 is equal to what as an Ohm's law relationship for me? What's I1? Well, and yeah, I'm gonna say VA over Z sub 2. And VA is, so it's the node voltage at the plus terminal minus the node voltage at the negative terminal. Node voltage at the negative terminal is 0. Node voltage at the positive terminal is V1. So I'm gonna say this is V1 divided by Z2. And my Z2 is R plus ZL. When I write code for this, I would have just said ZL is J times omega times L. Right? And my code is in the notes. You can take a look at it. Okay. So I do that. Then I do for myself, can I do a similar one for I2? I2 being here. Oops, I just noticed that I wrote that opposite right there. Can I define I2 like that? Like I just did? No, right? Because I don't have an Ohm's law that I can write for a voltage source. Like we said for the voltage source just takes whatever the circuit tells it needs to take. All right, so there's no way to make a relationship that constrains the voltage and the current in some way. If I have an impedance, then there's a constraint linking the voltage and the current in some way. There's no constraint for a voltage source. For what? This? Yeah, there's no way for me to define I2 related to VX. There's no way for that to ever happen. There's no constraint for that. All right, what about for these guys? So I3, I can do. I3, I write in terms of the voltage across that resistor. I called that V sub B, right? And I'm just going to put that over R, right? I called it Z sub R down at the bottom. I called it R at the top. All right, that's equal to, so the voltage across it is VB. The voltage, the node voltages there are V2 minus 0. V2 minus 0 over R. I4, which is the current in this branch over here. All right, this is I4 over here. How would I write that one? And just in terms of my Ohm's law relationship, what would that be? VB over Z1. Yeah, VB over Z1. So Z1 is what? It's, yep, V2 minus 0 again. And Z1 would basically be R plus Z sub C. All right, and I just like calling them Z sub C, Z sub L. I do not like to start putting in numbers like J6 or negative J6 because I've lost, at that point, I've lost my ability to look at the circuit and map back to what I'm seeing. All right, it helps me to keep it symbolic because I can always map it back to the picture. Once it becomes numbers, it gets a lot harder for me to map it to a picture and to check to see if I'm doing the right thing. Because I guarantee you're going to make mistakes when you're putting that stuff in there. And when you're debugging your thinking, you're going to have to go back and forth. All right, I wrote all that stuff. What's the next thing for me to do? I got to write my KCLs. How many KCLs do I need to do here? 1. Now I could do 2, right? I could do 2 and do it the same way that I did before, right? So if I did 2, based on the picture that I drew here, I could do a KCL at node 2 and node 1, right? And so what would it be at node 1, just to check? In terms of what I have here, how would I write my KCL at node 1?
I think we need to go to I1 plus
At node 1, if
sorry, I don't know.
well, yeah, maybe it does. It's I sub S. So basically what I have is at node 1, I would have I1 is going out plus I2 is going out and I sub S is going in. Right? That relates everything here. Similarly, I could do the same thing here and combine them. Solve one of those 2 equations for I2, which is the current through the voltage source, and combine them. But like we said previously, is I don't need to go through that process. I could just write them for the supernode. All right. So what did I do? Wow. That was a new one for me. I don't, did you get, does that appear there? Or is it, okay, all right. That was weird. Yeah. Doesn't matter. Just have to make sure I make whatever directions I want to, and I make sure that my equations are consistent. If I made that going negative, or made that arrow going that way, then the only thing that would have changed about my KCL is that I2 would have been on the other side. You just got to make sure the equations you write are consistent with the directions you drew. That's why it's important to draw directions. I see people don't typically put directions on there, and they're trying to keep track of it in your head, right? Don't keep track of it in your head, right? Go slow to go fast. That's basically the way that it works, all right, when you're trying to do this stuff. All right, if I wanted to do this for node 2, what would it be for node 2 based on the way I drew this? Ike, you can't talk. All right, what would it be for node 2? Here. I2 is going in. I3 and I4 are going out. So I2 for node 2, we have I2 equals I3 plus I4. Like that. Now I could combine those 2 together. Weird. It's freaky. I don't. There we go. Somehow worked before when I did that. All right, anyway. Sorry. All right. So, oh boy. So let's just oh goodness. Sorry, this is weird. It's freaking me out. Yeah. All right. Yeah. Oh my goodness. This is freaky. I might have to go this back to the board for this. Hey, and see how you. Okay. All right. All right. Wow. All right. All right. I1 was equal to V1 over ZL plus R. All right. Oh, wow. This is bad. All right. Oh boy. Very bad. Yeah, I think I need a new computer. Well, that's one option, but I actually think I need a new computer too. I cracked the screen. I think that could be fine. Yeah. All right. I1 equals V1 divided by ZL plus R. All right. And I had that I3 was V2 divided by R. And I had that I4 was equal to V2 divided by R plus ZC. Now, I wrote on that previous slide, if it kept itself, which it didn't apparently, I wrote the KCLs at each individual node, but I want to use the supernode relationship here. Okay. How do I use the supernode relationship in terms of I1, IS, I3, and I4? We said that whatever current, basically we said at node 1, I have I1 leaving and I2 leaving, and that has to equal I sub S, right? And then at node 2, I had I2 going in and I3 plus I4 going out. I could combine those into my supernode relationship. But the whole idea of the supernode relationship basically was that whatever is coming into one side of that voltage source is going out the other side of that voltage source. So how do I write the currents there without combining these two equations? How do I write them for the supernode? I could combine these two right here. Solve, in other words, I could say plug in I2 right here. So I2 equals I3 plus I4, plug them all in. Or I treat them all as one giant node. So if I did that, how would I do this? I wouldn't include I2. I would say the sum of the currents entering the supernode equals the sum of the currents leaving it. So based on the way I drew this, what are the currents going into the supernode? IS is the only one going in, yeah. All right, IS is going in. Okay, and what's coming out? Yeah, everything's coming out. So I1, I3, and I4. So if I took these two right here, here's my node 1, here's my node 2, and I combine those two relationships. Here's node 1, here's node 2. I would plug in this equation, I2 equals I3 plus I4, plug it in there, and I get the same thing, right? I get I1 plus I3 plus I4 equals IS. Right? Same relationship. Okay. Now, what do? I basically go to this guy here and I say I sub S equals, and I plug in those relationships. V1 over ZL plus R plus I3 is V2 over R, and I4 is V2 divided by R plus ZC. So step back in this thing. If I want to make this thing work, how many equations do I need here? 2, because I got 2 unknown nodes. This is 1, and it's got 2 unknowns. What's the other equation? It's the one that comes from KVL, right? So it better be just in terms of voltages. What's the KVL relationship that I get in this case? Vs is V1 minus V2. I've got 2 equations and 2 unknown. Okay, now what I do is I put this into matrix form. And the way that I do it, let me see, I put my code here. Yeah, so let me just try to make sure I'm consistent with my code as I write this. Okay. All right. So Vs equals V1 minus V2. That's an equation for me. I want to get this into the form where it looks like this. A1, A2, A3, A4 is V1, V2 equal to something over here. All right, that's the way I try to approach this thing, and I get it in there like that. So, in other words, you guys should know then, basically, if I look at this, A1, V1 plus A2, V2 equals something. I should be able to get that from my equations, and then A3, V1 plus A4, V2 equals something, okay? So what I typically do is I'm going to look at the 2 equations like this. All right. This equation here, I'm going to make that my first equation. Okay. So that is IS equals V1 divided by R plus ZL plus V2 divided by R plus V2 divided by R plus CC. I think that's right. Yep. Okay. How do I put that in matrix form? Here's how I do it. Is I basically say, I group all my terms like this, and I say, all right, I have 1 over R plus ZL times V1 plus 1 over R plus 1 over R plus Z sub C times V2. You guys follow me? Now, what I'm going to do in my MATLAB is I'm going to say, all right, this will be A1. This will be A2. That way I can look at everything nicely, all right? And I can review everything. So over here, what do I put on this side of the matrix? What's it equal to? Well, it's I sub S, right? Yeah. Which I sub S we had said previously was, we go back, it's 2 angle 0. Okay. And then the other relationship that I have is the one that is relating the 2 voltages. So Vs equals V1 minus V2. So I would have Vs here, and I would have A3 equal to 1 and A4 equal to -1. And I'd put it together like that. Okay. Now, again, I put this in some of the previous notes, so you go back and look at this, but this is how I enter that stuff in MATLAB. These are the key commands that I use, and this is the code that I ultimately use. Okay. So this has the same exact setup as what I had on the previous slide there. And so notice what I did here is I defined things like ZR, ZL, ZC, and then I just wrote my relationships in terms of those things. And then you'll notice then with my A1 and A2, right? I can always look at this and match up everything to my equation. I like that. I like being able to match my code up to my equations. So if I make a mistake, I'm not looking at numbers. I'm looking at a formula written down that matches the formula that I have written down on paper. All right, allows me to track more carefully. All right, so what I end up with in this basically is this. I'm gonna get a matrix from this when I go through this. And the matrix is gonna be V1 and V2. Okay. Which this is when I took the angle and the magnitude. So I got 5.7266. Angle negative 9.5588 degrees. And I got 77.588 angle. Oops, that was my angle. Yeah. 2.0981 angle 77.588 degrees. 5880, just to be clear. Helps me. Right? What this is saying is if I want to access those numbers, right? So what would I do? I would say V of 1 would end up being this value. V of 2 would end up being this value. Okay. And so what that means is if I wanted to look at the voltages as a function of time, this is what they would look like. In the real world, if I took an oscilloscope and plugged it in at node 1, the voltage I would measure would have an amplitude of 5.7266. Frequency would be 100 radians per second because we knew that. We did all of our analysis 100 radians per second. And then we said the angle would be negative 9.55. Okay. Similar for the other one. And so that code is here. And you guys can play with that code, right? Now, what we're going to do in recitation is we're going to do a number of examples. So this is one I'll probably start with there, which is the Thevenin equivalent where I've got some dependent sources. All right, so we'll look at this and some other stuff in recitation and problems that you guys want to look at. So we'll see you in a little bit. Oh, and before you guys